Today we're testing something that I've always wondered. Does adding more fins to a rocket actually make it fly better? And if it does, why don't big rocket companies use the same design? By the end of this video, we'll have some answers. Before we start cutting plastic and firing rocket engines, let's see what fins actually do. A rocket without fins is pretty much just throwing a dart backwards. The heavy end is in the wrong spot and it just doesn't work. Fins fix that problem. They shift the center of pressure, the point where aerodynamic forces act, behind the center of mass, the rocket's balance point. That's what keeps it pointed in the right direction. In my rocketry, the rule of thumb is to keep the center of pressure at least one body diameter behind the center of mass. That's how you get a stable flight. If those points are too close together, the rocket will wobble. If the center of pressure moves ahead of the center of mass, you're in for a very rough flight. So in theory, adding more fins to the body of a rocket should push the center of pressure back, making the rocket more stable. That's at least the idea behind this experiment. But here's the catch. Stability isn't the only thing that matters. If there's too much stability, the rocket becomes sluggish. It won't respond to small aerodynamic corrections. Bigger rockets need small corrections so they can point where they need to go. Plus, more fins equal more weight, which equals more drag. So you have to strike a balance. And that's why this test is interesting. On paper, adding fins should help, but in practice, it could make things worse. And there's only one way to find out. We start with the basics, designing a rocket motor tube that fits the Easties C6-7 engine. The first design we made and printed was way too loose. The second design, still too loose. So for the third design, we decided to make it much smaller, but we made it too small. The motor wouldn't fit inside the body. This felt like Goldilocks in the three tubes. Nothing was just right. So I went back, triple checked my measurements, and finally, we got one that actually fits. Now for the fun part, infinite stackable fin cans. It's basically just a system where you can stack fins on top of each other over and over and over again to see how it changes flight. The first print, it didn't fit. The second print, it still didn't fit. By the third design, I was questioning if I still wanted to continue with this project, but we finally got one. That meant it was time to print a lot of them. Next up is making it look good. I masked the fins with blue tape so I could spray paint the tubes without having the fins getting covered. All I used was Krylon's paint and primer. Not because I wanted that, that's just what they had in store. And now for the most satisfying part, peeling back the tape. Unfortunately, the paint bleed through was worse than I had hoped for. But hey, Sharpies fix everything, right? After sanding out the inside and gluing everything together, we finally had a fully completed rocket. On launch day, I brought the pad out to the field so I could get ready. I set the pad down, clipped the igniter in, and got the rocket ready. This was heavier than any rocket I've launched before, and the motor that was powering it, the Estes C6-7, didn't have much power. Alright. Okay, we are launching in 3, 2, 1. No! So there goes the rocket. The rocket started by lifting off the pad, but it wasn't flying straight. And when it came down and hit the ground, disaster struck. The fins had actually softened and warped from the motor heat, which I didn't account for. And to top it off, the rocket snapped in half on impact. So we couldn't launch again. The rocket was a one and done. So what happened? Why did more fins make this rocket less stable? One was weight. The rocket was way too heavy. This exact motor worked great on our Taser rocket that we did in a different video. But that rocket just weighed 41.4 grams. The new rocket, the one that we made in this video, weighed over 70 grams. A heavier rocket with the same thrust just doesn't go anywhere. The fins weren't perfectly straight. Even a small angle difference between them could mean that the rocket was unstable, which is what happened. The third major one is heat. I didn't account for the rocket motor getting so hot, and it got so hot that the motor itself made the rocket warp. The PLA plastic that we used is not made for high temperatures, which ended up causing the rocket to warp and bend and become unstable. So we tested it, and more fins don't actually make our rocket fly straighter. But what about the big rockets? The Falcon 9, the Atlas V, and the Ariane 5. Why don't they just slap on a ton of extra fins to make them go straighter? Turns out there are some really good reasons. First off, more fins equal more drag. Every fin creates surface area, and every surface area creates drag. That drag slows the rocket down, meaning the rocket either can't carry as much weight to orbit, or the rocket will just have to go slower. That drag slows the rocket down. So either the rocket can't carry as much payload, or the rocket has to carry more fuel. And when you're talking about multi-million-dollar launches, every kilogram counts. Number 2 is their weight and efficiency. Fins aren't just weightless, no matter how much you want them to be. On a small scale like mine, the weight difference isn't a big deal. But on a real rocket, even a few kilograms can mean the difference between making it to orbit or falling short. Companies like NASA and SpaceX are obsessed with shaving off every gram that they can. Adding more fins to the rocket just makes it heavier, slower, and sometimes even less stable. It's like asking Usain Bolt to run in the Olympics with ankle weights on. Number 3 is diminishing returns. That's the big one. Stability doesn't scale up linearly. Adding one fin makes a big difference. Adding a couple more fins will also make a big difference. But when you start adding 6 or 8 or even more, it becomes obsolete. At that point, you're just making the rocket heavier, slower, and even less stable than if you just had 3 or 4 fins. And here's the kicker. If even one of those fins is slightly off, it can mean the whole rocket is unbalanced. With 3 or 4 fins, that's manageable, but with 10 or 20, that's just asking for a disaster. So instead of slapping more fins on a rocket, the big companies use smarter solutions. Most of them use thrust vectoring control, where they bend and turn the engines to steer the rocket in the direction they want to go. Some rockets use grid fins, like seen on the Falcon 9 or Starship rockets. But those are only used on reentry. They're stagnant during the ascent. Reaction wheels and RCS thrusters are used in space where fins wouldn't work, since there's no air. So what do we learn? More fins don't actually mean the rocket flies straighter. Sometimes it can actually make it fly worse. But this experiment was still a success in my book, because any experiment that you can get information from and learn from your mistakes is a good one. Next time, I'll try a lighter design, a more powerful engine, and different materials for the fins. If you enjoyed this experiment, make sure you like and subscribe so you don't miss the next one. And remember, stay curious and aim for orbit.